Thanks to organizers for inviting me. Well, my name is Gustavo Angulo. I'm going to present joint work with Diego. Okay, this is like a standard integer programming. I will talk about the TSP, which is a well-known combinatorial problem. So we will have a directed graph G with which will be complete for our purposes, and we have a cost vector, and we want to find Hamiltonian cycle of minimum cost, right? So this is the typical problem. So we will talk about different formulations for this problem. So the base formulation that we will consider is an arc-based formulation where we have x variables xij, denoting if arc ij is part of the tour. So we have the typical, here we have the objective function. We have some out-degree constraints, in-degree constraints, integrality constraints, and this part which eliminates the subtours, right? So we know that if we consider only 2, 3, and 5, this is not a valid formulation because we can have subtours. And these three constraints, if we consider the linear relaxation, we have a phase of the assigning polytope. And I will denote that particular polytope PAP for assigning polytope. That will be part of the talk, okay? Good, so if we want to formulate the TSP, we have to somehow represent this constraint. And there are several ways to do so. Just a bit of notation, we will use node 1 as a special node just for modeling purposes. This is without loss of generality. So N is the set of all nodes. N1 is the set of remaining nodes after we remove the first one. A1 will be the set of arcs among the nodes different than 1. Then we have the set of cycles over A1. So these are all the cycles that don't go through node 1. And here S1 is the collection of subsets of N1 with at least 2 elements. Okay, so probably the most classical formulation for the TSP is the Dancing-Fulkerson and Johnson formulation, which has an exponential number of inequalities, which are called the clique inequalities, that have this form saying that for all subsets of nodes, or most of them, if we consider all the arcs connecting the elements of S, and we count the number of arcs between these elements, that cannot be greater than the number of elements minus 1. So this is the typical formulation, and this one is very, the linear relaxation is very strong, but is exponentially large, I mean in the X space. So there are other formulations that use additional variables and constraints, which are called extended formulations, right? I will review 3 of them that will appear later in the talk. So the simplest one is the Miller-Tucker Semlin formulation, where we have additional variables UI. UI kind of denote the position of node I in the tour, right? So if we have if xij takes the value 1, it means that I and j are consecutive, and therefore the position of node j has to be at least 1 more than the position of node I. So this is the relationship. Note here that in general we can understand UI as an integer variable taking values between 2 and n, but that is not really required for the formulation to be right, okay? Then we have the Rocher and Laporte formulation, which is an strengthening of this one, where we include this additional term, right? In this case, when we consider this constraint for ij and ji, the reverse arc, both imply that if we use arc ij, then uj is exactly ui plus 1. It's a bit stronger, right? Good. And the other one, and the last formulation that we will consider is the single commodity flow, where we have additional flow constraints for, flow variables for all arcs and constraints for all nodes. So the intuition here is that the first node is kind of a supplier, so supplying minus 1 units to the remaining nodes, which can be understood as clients, and each client has a demand of -1, or 1 actually. So these constraints imply connectivity, okay? Because when we have subtours, we have a disconnected graph, and we want to avoid that, okay? So this implies connectivity. Good. So we have the, 3 extended formulations: U variables here, U variables here, F variables here. So if we want to compare the strengths of these formulations, we have to project them onto the X space, okay? So if we project the Miller-Tucker sampling formulation into the X space, we recover what are called the weak circuit inequalities, okay? So here we have the sum of the arcs over each cycle. If we project the Rochert and Laporte formulation, we get a strengthening of the previous inequalities, which are called the least weak circuit inequalities. Here, we also have the arcs in the reverse cycle, multiplying by some factor. And if we project the single commodity flow formulation, we get the weak clique inequalities, where we have in the left-hand side, we have all the arcs between the elements in S, but we have something that is not as strong in the right-hand side. Okay, so these are well-known results. This is very well-known. Okay, so let's try to kind of generalize the Miller-Tucker sampling formulation, and this is the main idea of the talk. So when we look at these constraints, we are kind of saying that when we think of the U variables as labels, okay? So this constraint is saying that the labels have to increase at least by 1 when we go from node I to node J, right? But there's no reason to say that the difference between the labels has to be exactly 1. It can be any positive number that will give us a valid formulation for the TSP, right? Any positive number. Good. So in that sense, instead of having a 1, we could have any positive number here for any ij, and consider m as a big constant. So if we use the arc ij, this goes away, and then it's saying that the position or label of node I has to be strictly greater than the label of node I, right? So if you consider then any cycle, then the positions or labels have to be increasing, and therefore we cannot have cycles over A1. So this is another valid formulation. And notice that we have, for any choice of a positive vector D, we have a different formulation, and all of them are valid. Okay, so we kind of want to study maybe the differences or similarities between different choices of this parameter D. Okay, to do so, we will normalize, and we will take this big M as 1, and we will define the set capital D as the set of all distance vectors that provide us a valid formulation where, when we take M equal 1 as this big M constant. Okay, so if we take any D from this set, then this formulation is a valid formulation for the TSP. Is that clear? That has to be. So this is the main idea. So we have here a family of formulations for the TSP. One formulation for each choice of D in capital D. Okay. Notice here that I forgot to mention that R++ is for positive numbers. Okay. So to have a valid formulation, we need positive numbers here. Okay. I will denote D bar as the topological closure of D, which will be a polyhedron, right? Including the possibility of having D equals 0 for some components. Okay, so here we have again our extended formulation. We have X and U. X has to satisfy the constraints in the assignment polytope, and the vector U together with X have to satisfy these constraints for all arcs. Good. So this is kind of, I was thinking of the previous talk. We will have kind of a replication scheme here, because I will go through the Miller-Tucker sampling formulation in more detail, and kind of this similar results we will have also for the Rocher-Laporte formulation and for the single commodity formulation. Okay, so we will start with this extended formulation. We will project it into the X space. We will look at that formulation, and then in the X space we will compare the formulations that we get for different choices of these parameters, D or D prime in capital D, and in most cases these two formulations will not be comparable, and so we can define what the closure of this family of formulation as taking the intersection of all of them in the X space, and we will study that set as well. Okay, and we will kind of do the same for all three formulations: Miller-Tucker sampling, the Rocher-Laporte, and single commodity flow. Okay, let's get started with this. So in general, I will denote with letter Q something that is an extended formulation, and with P what is the projection in the X space, right? Good. So I will define P as the projection of Q. So the first result is very simple, that if we project this extended formulation into the X space, we recovered this set of constraints. Okay, so if you recall the weak sequence inequalities, notice that the left-hand side is the same, but instead of having this term, which is a constant, is basically the same for all cycles. Here we have something related to the choice of D. So this is kind of a generalization. And something that is very important here is that the term D only appears in the right-hand side. Okay, so that's simple. I also mentioned here that even though we need D in capital D to have a valid formulation, I will also consider D in the closure, because I will need that for later. Okay, so all these results also hold for D in the bar in the closure. Okay, so we have this set, and we can characterize when these inequalities are facet defining for this particular formulation. Okay, so for this inequality to be facet defining, we need that this term has to be positive, and the cycle has to exclude at least one node from N1. It cannot be the longest cycle. Good. So this is kind of there are many things that I forgot to say here. So recall this set, and D bar is the closure, which is a polytope. Notice here that this set has an exponential number of inequalities, one for each cycle. We can show that linear optimization over this set is NP hard. Okay, so in general, it will be hard to separate over these inequalities, and also characterizing the vertices or enumerating them will be hard. What else do we know about this? And all these inequalities are facet defined, and this set is full dimensional. We can get a reduction from the TSP itself, basically. Oh. Yeah. Good. Okay. Now we want to compare what happens when we pick different elements. So with this one, the first part of this proposition says that if we take D and D prime both in the interior of this set of parameters, the formulations that we get are incomparable. Okay, which is kind of interesting, because when we started this project, we kind of thought that that the classical Miller-Tucker assembly formulation was kind of the strongest, because maybe it was in the middle of this set, right? Because the parameter D is 1 over n minus 1 for the original version. And it turns out that everything that is in the interior can be is not comparable with any other choice of the parameters. Okay, so if we try to get something that is not dominated by anything else, we have to be in the border of the set, right? So actually, if we pick say D and D prime in different phases of the set D bar, then sorry, I said something. I was imprecise. Sorry. If we pick D in the interior, then we can choose another D prime, which give us a strictly better formulation than D. Yeah. So if we want to get formulations that are not comparable, then we need to pick parameters in different facets of the set D, capital D. Okay. And then the formulations are not comparable. Actually, we have something that is quite interesting here. So DMTC is the set of parameters that define the classical Miller-Tucker formulation. Okay, so if we take that particular choice of D and we perturb the vector with an antisymmetric vector, then if we have something, if we try to get something better, a new formulation that is contained in the original classical formulation, then actually we cannot. Both have to be the same. Okay? So in general, there's no hope for getting very different things coming out here. Good. What else here? Okay. Notice here that in principle, we could choose we could include different choices of our vector D, and we could have extended formulations for different subsets D prime of D bar. What I mean here? Suppose that in D prime I have one single element from D that gives us one particular choice of a formulation. But maybe we could have several choices of D at the same time. But notice here, and this is very important, that we will need one different vector U for every choice of D. Okay, so say that we have K, if in D prime we have K vectors, D, we have D1 up to Dk, then we will have to be then we'll need to have variables u from u1 to uk. We need different vectors u for different choices of parameter d. Okay? Well, in principle, actually, we could have infinitely many vectors d here. So this could be kind of an external formulation with an infinite number of additional variables, which are functions in reality. Okay? So the point here, the main message here is that we can have elements in the boundary of d prime as long as the whole collection of elements that we are considering here, the collection of parameters, satisfy this for some choice of d in d prime. Okay, and if d prime is a finite set, then we get like a regular extended formulation with a finite number of additional variables and constraints. Okay. Good. Okay, so I just said a few minutes ago that the set d bar is kind of a complicated set because it has an exponential number of constraints which are hard to separate, and the vertices are likely to be hard to characterize. I will focus on a particular choice of vertices of d bar, which are very simple. For each node in N1, consider the vector where we have a value 1 for each arc that is coming out from node I, and 0 for any other arc. So this is kind of a star. So you pick node K. For all the arcs that are going out from node K, we will take the value 1, and all the remaining arcs will have value 0. Okay, that particular vector d is within d bar, and actually is a vertex of d bar. Okay, and we have one vector for each element in N1, so we have n-1 vertices of d. Clearly, this is not the complete set of vertices of d bar. Okay, but we can show the following. So CL denotes the closure, which means intersecting all the formulations. So it means here we have the following result. Suppose that we intersect all the formulations given by all possible choices of d in capital D. Or consider the intersection of all formulations given by these particular choices of d. Here, notice here that we are intersecting n-1 sets. Here we have an infinite number of sets, and all of them are, and these two intersections are the same, which we call p bar, and this formulation p bar is this one. Okay, this is kind of expected in the sense that if we think of kind of robust optimization, if we want this constraint to hold for all choices of d, we will have to minimize the right-hand side, which accounts for maximizing this term, and the maximum of this term is precisely 1. So this is kind of simple in this case. What is interesting here is that these constraints are called the circuit inequalities, which are stronger than the weak circuit inequalities. Here now we have a 1 instead of this factor here, right? So this formulation arises in a paper by Pires and Guedia, and this is quite interesting. In their work, they took the Miller-Tucker sampling formulation and they proposed a disaggregation of the variables u. So in the original MTC formulation, the u variables are kind of integer, taking value from 2 to n, right? So in their work, they write these u variables as the sum of some binary variables, giving a disaggregated version of Miller-Tucker sampling formulation. And they show that this disaggregation gives rise to circuit inequalities. Now we have shown that the same circuit inequalities arise as intersecting all possible choices of these generalized Miller-Tucker sampling formulation, which is kind of interesting because there are two ways, at least, of getting this stronger formulation. Okay, so there's a connection there. And actually, if we apply this this result for D prime being exactly this set, we get an extended formulation with these additional variables and constraints, which are exactly the same. This is exactly the same extended formulation given by Gouveia and Pires. The same, but the way we get these formulations is completely different. Okay. Questions so far? Good. Okay, now the replication. Let's play the same game for the or a similar game for the Rocher and Laporte formulation. Let's go back for a bit. So this is the renal the Rocher and Laporte formulation. Notice here that the n is related to the big M that we will consider appears here, here, and here. So after thinking a bit, we propose this kind of constraint as a natural generalization for the DL formulation, where again the D has to be a positive vector and M has to be a large enough constant. If we normalize, taking M equal to 1 and D being in the set capital D, we get this generalization of the DL formulation, right? So M is 1 here, and also 1 here, okay? And D has to be in capital D. Notice here that this time, this formulation is a bit different from the previous one, since D not only appears in the right-hand side, also appears in the left-hand side, multiplying X, okay? So again, we can project, and naturally, in the projection, D not only appears in the right-hand side, also in the left-hand side. Okay, so this is the projection. Notice here that we have a set of constraints that are independent of D. These are for circuits of length 2, and for everything else, we have this collection of constraints. So now the analysis becomes a bit more. It has more details because we have to deal with the left-hand side. Again, we can characterize the facet of this set. Again, we need this to be positive and C not being too large. Okay. Good. Again, we try to analyze what happens when we pick different vectors D as parameters. Again, if we take one D in capital D and we perturb that vector with an antisymmetric vector, which in some cycle is not null, then again we get two formulations that are not comparable. Okay. Again, we can get valid external formulations from this set. Always, we can include several choices of D at the same time, including these in the border of bar D. The main component, the main ingredient to get a valid formulation is that for some element in D prime, every the sum over a given cycle has to be positive. We need this to exclude the particular cycle from appearing as a subtour in the solution set. Okay. Good. Again, if we take a D prime satisfying this condition and having a finite number of elements, we will get a regular external formulation with a finite number of additional variables and constraints. This time, we will look at this particular set of vectors, which will be all the canonical vectors in R to the A1. So we have each of these vectors is a bunch of zeros, and we have only one arc, one per arc, right? So the number of vertices that we have here, or the number of elements that we have in this set, is precisely this number, which are also vertices of D bar, but again, these are not all vertices, right? So turns out that if we want to intersect all these generalized formulations and get the closure, it is enough to consider only the formulations given by this set of vectors, okay, which is a quadratic number of elements. And when we consider the intersection in the X space, we recover these constraints. Yeah? So notice here that in these constraints, we are summing the arcs in the cycle C, the arcs in the reverse cycle, and we are subtracting one term. That happens. That's what's happening. Something that is interesting here is the following. So, in the work by Pires and Guedia, they propose a lifting of their disaggregation, and they say that this lifting is a disaggregation of the Laporte and de Rocher and Laporte formulation. Okay, and they get something very, very similar to this, but instead of subtracting one term, they end up subtracting two terms. That's the difference. Okay, so it's almost the same, but it's not. It's slightly not. And actually, what happens here is that if we consider, instead of considering these vertices, we consider the vertices from the MTC formulation, then we recover the lifting by Pires and Guedia. Okay, so there are some subtleties, and again, if we consider the closure, the closure of the DL formulation, we get a slightly strengthened version of the lifting by Pires and Guedia, which is very, very mild. Good, and again, I notice here that we are not really discovering new formulations, but we are recovering well-known formulations, but from a different point of view. Okay, and even the external formulation that we get here is basically the same as what we get in their paper. Good. Last replication. This time for the single commodity flow formulation. Now we have to change the set of parameters, because this is a flow-based formulation, not a kind of a position or distance-based. Okay. Okay. So the generalization here is the following. So in principle, in the original single commodity flow formulation, we have here an n-1 and a -1 here. So what we do now is that for all the nodes that are different from node 1, which are kind of customers, we will have a positive demand. And therefore, the supply from node 1 has to be equal to the overall demand, which is positive. So we have here the positive demands, we have the overall supply, and we have the kind of the same BGM constraint here. Again, we notice that that any choice of a positive demand here will lead to a valid formulation for the TSP. Okay, so again we normalize and we take m equal to 1, and we arrive at to the set capital V, where we have positive entries summing up to 1, which are the kind of the demands of the remaining nodes. And therefore the generalization of the single commodity flow is as follows. We have these balance constraints, and notice here that we are not taking into account the first one, because the first one is redundant given the remaining constraints. Okay, recall that in this flow formulations, there's always, we can always eliminate one of the flow balance constraints because it's redundant given the others. Okay, so we have these constraints and these variable upper bounds. Good. So again, we can project. If we project onto the X space, we get this kind of formulations. Again, notice here that the parameter B appears only in the right-hand side, so therefore the analysis is simpler than in the DL formulation, and this is a generalization of the width-click inequalities, right? Notice here that we can already see that, as in the MTC formulation, if we want this to hold for all B, for example, we will have to minimize the right-hand side. Therefore, we will have to maximize this term, and this maximum will be 1. So we can already see that. Again, we can characterize all the facets of this set, and again, we need this value to be 1, and the set S not being the complete set N1. Something that is very interesting here is that for any choice of different B's, the formulations are different. There's no way to have the same set, and they are never comparable. Okay, so therefore now it makes sense to intersect all of them, because everyone will give us something different. So again, we can construct this, extended formulations, as long as if we pick several choices of elements B, we need for each node to have some positive demand for some element in B prime. Okay, and that will give us a valid extended formulation, hopefully with a finite number of variables and constraints. In this case, to get a regular extended formulation, we consider the canonical vectors, one per element in B bar. In this case, notice that B bar is basically the simplex, right? We have non-negative entries summing up to 1. We know that we have one vertex per coordinate, so we have n-1 vertices, and the set of vertices is precisely this set. And therefore, if we consider the closure over the whole thing, it's enough in this case to consider the closure intersecting the formulations given by this set of parameters, and we get this. And once we see this, these are precisely the click inequalities, which are the inequalities that define the Dantzig-Fulkerson and Johnson formulation. Okay. We also know that this formulation is equal to the projection of a multi-commodity flow formulation. And actually, if we take these using this set of vertices, we do recover the same extended formulation, which is called the multi-commodity formulation. If you think about it, the multi-commodity formulation is kind of a disaggregation of the single flow formulation. Okay, And we arrive kind of to the same result, but instead of explicitly disaggregating, we are intersecting all the choices for the single committee flow formulation, and we arrive at the same result. Good. So these are the results for all the cases, and our conclusion here is that if the graph is small enough with 4 nodes, all these things are the same, right? But if we have at least 5 nodes, all these things are different, and they are strictly different. Okay, being the single committee flow being the strongest, and the mirror target sampling being the weakest. Okay, so we have here a strict hierarchy. Good. So this is what I wanted to share with you. We have some ongoing ideas to extend this. One natural idea would be to look for other combinatorial problems where some parameter works for a classical formulation, but maybe other choices will do also, and we could try to generalize that too. Something else would be to try to use this computationally, in the sense that typically when we solve an integer program, we solve a relaxation, we get a fractional point, and we try to find a most violated cut and add that, right? In this case, we could try the following. We will start with one single parameter, d, say. We get a formulation, an extended formulation, we solve for that. And given the fractional solution, we could try to extend the extended formulation in the sense of including one additional parameter, d, another one, that cuts this particular fractional solution. The thing is that enlarging the extended formulation maybe will cut a bunch of points, because it's really adding many inequalities in one step, right? Because after we project, we get a bunch of inequalities. So there's an interesting question of how to select that extension of the extended formulation so that computationally sort of efficient way. We were not sure how to define the kind of the most violated cut in this case. So that's what we plan to do in the future. So thank you for your attention, and I can take any questions.